We're going to continue our study of vectors in section 7.5, but we're going to try to get away from the picture drawing and represent them in a different way to make operations with them easier. So our first definition, which is long here, but it's a very simple idea. It says a vector with its initial point at the origin in a rectangular coordinate system is called a position vector. Rectangular coordinate system is your usual XY, okay? The Cartesian plane. Okay, so let me see. So a vector with its initial point at the origin. So the initial point of a vector is here. It doesn't say anything about the terminal point. The terminal point could be anywhere. I'll just put in the first quadrant. Okay, so this is called a position vector. So instead of having vectors just floating around the plane, we're trying to give them some sort of reference point. So a position vector starts at the origin in the xy plane, and the terminal point can be anything. So this is called a position vector. A position vector U with endpoint AB. Okay, so this point right here, we're calling the point AB. Okay, so it starts at 0, 0 and ends at the point AB. We write this vector, if I call this vector U, we write the vector U as bracket AB. Now let's talk about the difference here. Parentheses AB, parentheses, refers to the point where it stops. That's a single point. The bracket AB is the vector that starts at 0, 0 and stops at the point AB. Notice you don't have to do something indicate the initial point, because the initial point is 0, 0. We know this. So the coordinates of the terminal point are right there, AB. So it starts at 0, 0, ends at AB. So this notation means vector. The numbers in B, this is called the x component and the y component, no problem. The positive angle between the x-axis and a position vector is the direction angle. So the direction angles here, just think a direction angle is angle in standard position, and it says positive angle. So a direction angle is start from initial your positive x-axis and rotate around. Don't go down, right? It's always positive. Okay, so when they say direction angle, they always mean standard position, basically. Okay, so let's look at an example here. Number 10 says, find the magnitude and direction angle for the vector minus 724. When you write your vectors, make sure you're writing them with the brackets and not parentheses. Parentheses means a point. Magnitude and direction angle. Okay. Now the good news is, pretty much everything in this section, at least this first part, we already know the math. We've already done the math. The only new thing here is this new vocabulary. That's the only thing that's new, right? We didn't, a few sections ago about what is this? What do we do with this? But what is this just begging for you to do? Draw the picture, right? Let's draw a picture of this vector. So it's negative 724. So the terminal point is where? In the second quadrant. Okay, so it's rotating around to here, minus 724. It's up here. I'm not trying to get this to scale. And it's just begging for me to draw a triangle. So this right here is the vector, negative 724. What is it just screaming for you to do? What do we do every single time? X is negative 7, y is 24. I mean, there's nothing new here except for the notation. Now what the problem asks for, it asks for the magnitude and the direction angle. Where's the magnitude? The magnitude is the length of the vector. We've done this before. We did this on the first day of class, I believe. Or maybe second. Okay, so, I mean, we're looking for what we used to call R. If you call it R, again, I'm fine with that. I know what you mean. Right? But what is the actual definition? It's the magnitude of the vector. Remember, the vertical bars mean length of vector. So if you just want to call that R, that's fine. Okay? So how do we figure that out? It's that formula we did before. It's the square root of x squared plus y squared. Again, I didn't include the negative 7 because negative 7 quantity squared is the same as 7 squared. So what does that turn out to be? I think this is Pythagorean triple. Yeah, it's the square root of 625, which is 25. Okay? And label your work. Don't just write numbers like that and have floating numbers. Label what you're doing. I'm finding the magnitude, or again, R is the magnitude. Label your work. So there's the magnitude. Now we just need the direction angle, which I've already indicated here. There's the direction angle from here to here. That's what we need to find. Okay. I'm going to erase this. Okay. Now, it might be helpful to find what first instead of the actual direction angle. Let's find the angle in the triangle here. Okay, I'll just call that theta. Okay, so I'm finding the reference angle first. Now, I think we've talked about this before, maybe not. When you're trying to find an angle in a triangle in this sort of situation, ignore the negatives, and I'll explain why in a minute. So again, just think of this triangle as like this. So here's theta, here's 24, and here's 7. I'm ignoring the negative. If we wanted to use the 25, we could, but the point is we could have found this before we found the r, so I'm just going to pretend we don't have the r. Well, how would you figure out theta? It's a right triangle. What's the procedure? Choose an acute angle and two sides. We've done this before. And then what trig function relates that angle to these two sides is opposite and adjacent, so that's tangent. So tangent of theta is 24 over 7. Okay? So what's theta? Theta, tan of an angle is a number, so the angle is tan inverse of the number. And I'm just going to round the two, I'm going to do decimal degrees here. It didn't say to do it in degrees and radians or anything. I got 73.74 degrees. Don't forget your degree sign. You round to two places. All right, so to answer the question, what's the direction angle? Right, it's from here to here, all the way to here, it's 180, but you have to back up theta, so it's 180 minus 73.74 degrees, which is 106.26. Okay. Now, let me explain to you why I'm telling you to ignore the negatives when finding a reference angle like this. Okay. Suppose, okay, hopefully everybody has that, because I'm changing the problem. Don't change yours. Suppose I had left the negative here. Well, then you'd have a negative here and a negative here, and the calculator would have given you a negative here. Now, my guess is you would have said, oh, just ignore the negative and it's 73. Okay, fine. That wouldn't have been in the end of the world. But I want you to realize you're going to get a different answer that you have to think something about. Suppose, on the other hand, instead of doing that, suppose we had chosen the -7, assuming you left the negative there, and the 25. Suppose you had done that. Then you would have said that's adjacent and hypotenuse, that's cosine. So cosine theta would have been -7 over 25. Cosine of an angle is a number, so cosine inverse of the number is the angle. And you would have gotten cosine inverse of -7 over 25 is 106.26 degrees, which was the direction angle, not the theta. All right, so you realize this can't be the theta. That doesn't make any sense. So that's, notice whether I did sine or tangent. Well, I did tangent without it. Notice if I had done sine with 24 and 25, I would have been fine. The problem is getting a negative here, right? Notice with the tan we got a negative, and cosine I got a negative, and we got a funny answer. Right, that's why whenever you're just trying to find a reference angle, ignore any of the negatives. Just make everything positive. That's when you're trying to find the reference angle. Okay, well that was that one. Okay, the next definition, I'm just going to draw a picture. It says, okay, so before we do this, if I gave you like the number 10, and I said write this as a sum of two other numbers, you might say 9 plus 1, or 8 plus 2, or 6.5 plus 3.5. We don't just live in the world of integers, right? Or you could even say 11 plus -1. There are a lot of ways of rewriting 10 as a sum, right? There's an infinite number of ways to do that. Likewise, suppose I gave you a vector like this, and I said find two vectors whose sum is this vector. So in the previous section, it was here's a vector, add them together. Here's a vector, add them together. Here I'm giving you the sum, and I'm telling you to find two vectors that add up to it. Well, you could do, okay, so this is my original V, right? You could do this vector plus this vector, right? That plus that would be that, right? You started here and then ended up here. Or you could do this vector plus this vector. Or you could do this vector plus this vector, right? So like I did with the numbers, if I give you a vector V and say find two vectors that add up to it, you could find an infinite number of things. But what if I put a restriction on it? Just like adding the numbers, I mean, suppose I put restrictions and rewrite 10 as the sum of two numbers with some specific properties, you would narrow down the possibilities, wouldn't you? Same thing here. Suppose I give you, this is what I'm drawing in the picture here. Suppose I draw this vector u. That's playing the role of the v I had a second ago. And I want to write this as a sum of two vectors, one of which is horizontal and one of which is vertical. So I can't do all these weird pictures I was doing before. How could I write this as a sum of a horizontal vector and a vertical vector? I could do this for the horizontal. Do I call that anything? No. And this for the vertical. Isn't this plus this equal to that? Or I could have done it this way. I could have done the vertical here and the horizontal here, but notice the vertical here is the same. It's the same vector, and the horizontal here is the same. So it's really, that's the only way you can do it. Okay, so this is a horizontal vector, and this is a vertical vector. And notice my horizontal vector plus my vertical vector, oops, is my u. Okay, so that's all we've done here. So we're breaking up a vector into a horizontal part and a vertical part. So this length right here, I'm calling x. X is the horizontal component of u. And if I call this length y, y is the vertical component of u. Okay, so just the length of that and the length of that, those are your horizontal components and vertical components. That's all there is to it. Okay. Okay, the next example says, suppose the magnitude of v is 50 and theta is 20 degrees is the angle of inclination from the horizontal. In other words, the direction angle. Find the horizontal and vertical components of v. Well, let's draw a picture. That's shocking. Well, if theta is 20 degrees, we're in the position vectors in the first quadrant. Again, I'm not trying to get this to scale necessarily. So my angle here is 20 degrees, and the magnitude, this is vector v, the magnitude, the length is 50. Okay, so that's what this is saying. So then it says find the horizontal vertical components. It's finding the length of the horizontal vector and vertical vector whose sum is v. Well, the horizontal vector is here, the vertical vector is here. I call that and call that x and call that y. We're trying to find x and y. We're back to section 2.4 because this is a right triangle. We're solving a right triangle. That's all we're doing. So once you draw the picture and understand what these problems in this section are asking, you're going back and using math we've already done. Okay, so we're solving a right triangle, so I need to find x and y. Let's find x. I'm going to choose the acute angle and those two sides. I know two of them, so I can find the third. What trig function relates the 20 degrees to these two sides? That's adjacent hypotenuse, so that's cosine. Cosine of 20 degrees is x over 50. Cosine is adjacent over hypotenuse, or x over r. So if I multiply both sides by 50, I get 50 cosine 20 degrees is x. Okay, I'm going to go and do y so I don't have to get my calculator. Now, what if we're trying to find y? I'll punch this in a minute. So let me choose the 20 degrees, the y, and the 50. Right? So I know two of the three. What trig function relates the 20 degrees to y and 50? That's opposite and hypotenuse. That's sine. Sine of 20 degrees is y over 50. So if I multiply both sides by 50, sine 20 is y. So I'll punch these in. So 50 cosine 20. So x here is 46.98, two places, and 50 sine 20. That's y is 17.10. There's no units. I don't know what the 50 is. Does this make sense? Do the answers make sense? We said this vector, the horizontal vector plus the vertical vector is supposed to be the vector I started with 50. But 46 plus the 17 is not 50. Did we do something wrong? What's going on here? You have to be careful here. Notice, I didn't say x plus y had to be 50. That's not what I said. This vector plus this vector is 50. That's a true statement. I didn't, remember, x is not the vector, it's the magnitude. That vector, that picture, plus that picture is that picture. That is a true statement. That's a relationship between the vectors. That vector plus that vector is that vector. What's a relationship between the sides? Pythagorean theorem. So if you want to check to see if these answers make sense, is 46.98 squared plus 17.1 squared the same thing as 50 squared, and I'm off by 0.5. So yes, so we're okay. So be careful. I'm not saying the length of that plus the length of that is the length of that. That vector, the horizontal vector plus the vertical vector is the original vector v. But the magnitude plus the magnitude is not the magnitude. That's not true. Okay. Oh, okay, good. Now, in the last section, we were learning how to add and subtract and multiply vectors by a scalar, which was a pain drawing all those pictures, right? But in this position vector notation, if you have a vector AB plus a vector CD, we know a vector plus a vector is a vector. It turns out you just add the components, A plus C, B plus D. And to subtract vectors, it's obviously the same thing you would think. You subtract the components, A minus C, B minus D. And how do you do K is a scalar here. A scalar times a vector is the vector Ka, Kb. Whether K is positive or negative, it doesn't matter. So notice what we're doing here. We're learning how to add and subtract and do scalar multiples of vectors without actually drawing the pictures. Right? So you can add a bunch of vectors, get the answer, then draw the answer if you wanted to. Okay, so this is a combination problem of three problems here. It says, suppose vector u is the vector minus 2, 5. Vector v is the vector 4, 3. Okay, so it says find v minus u. Find vector v minus u. Let me write the other problems down. And then negative 5v, and then negative 2u plus 4v. Okay, those are the three problems here, using these u's and the u and v here. Well, v minus u, well, what does the definition say? A vector minus a vector is you subtract the components. Let me go ahead and write these down. Vector v is 4, 3. Vector u is negative 2, 5. So how do you subtract vectors? You subtract components. 4 minus negative 2 is 4 plus 2 is 6. 3 minus 5 is negative 2. So the vector 4, 3 minus the vector minus 2, 5 is a vector 6 minus 2. Now how do we do negative 5v? Let me write vector v here. By the definition, what do you do with the scalar? You multiply each component by the scalar. Negative 5 times 4 is negative 20. Negative 5 times 3 is negative 50. And make sure you're writing brackets for vectors. Okay, now this last one is a combination of the two. Negative 2u, 2, 5, plus 4 times vector v, which is 4, 3. See if you can do that one. Pause the video and finish this. So it's a scalar times a vector, so it's like this one, and then you have to add those two answers. So pause the video and do that one. And then I'll do it, we'll see if we get the same thing. Okay, so if we finish here, if I multiply the negative 2 scalar times both components, I get 4 negative 10. Plus multiply the 4 times both components, I get 16 and 12. Let me check. 4 minus 10, 16, 12. And then add vectors, you add component-wise. 4 and 16 is 20. Negative 10 plus 12 is 2. So it's the vector 22. Now, let's see if this definition even makes sense. Okay, this is not part of the problem. I just want to convince you this actually makes sense to do. Let's do this problem, v minus u, with the pictures we did in the last section. So I'm going to try to get a decent scale here. So vector v, u is minus 2, 5. 1, 2, 1, 2, 3, 4, 5. So minus 2, 5. So here's vector u. And then vector v is 4, 3. 1, 2, 3, 4, 3. So there's vector v. And we want to do v minus u. So I want to put them head to tail, right? The answer's not here. You have to put them head to tail by the way I've been doing it. So negative u is you switch the head and the tail, right? So negative, well, I'm not going to draw it. So let me move this to here. Again, this is just approximate. That's not bad. And notice I'm switching the head and the tail, so there's negative u. Okay? And so if I go from here to here and then here to here, the resultant is here to here. There's v plus minus u or v minus u. Okay? Now let me put in a scale here. So again, notice this vector starting at 0, what is the coordinates at that point? Well, my picture looks like it's about 7 minus 1.5. Again, my scale's not very good. But what was the answer supposed to be? 6 minus 2. It's close, right? It's supposed to be here, actually. But that's because my pictures. That's one advantage of doing this. I did it with pictures, and my answer's off a little bit. The actual answer should have been 6 minus 2. It should have been down here. Okay? All right, so it's reasonable. Yeah. See, notice my picture was inaccurate. That's what I should have done. That's why this is so much better. You don't have to draw any pictures, but it sort of makes sense. Okay, so the next idea is the dot product of two vectors, u and v, is denoted by u dot v, and it's given by, okay, so if you have a vector u dot vector v, so u is the vector ab, and v is the vector cd, and the formula is ac plus bd. So what do? You multiply the first components, you multiply the second components, and you add those two together. Now let's go back for a second. If you add two vectors together or subtract two vectors, what do you get? A vector. Right? A vector plus a vector is a vector. A vector minus a vector is a vector. A scalar multiple of a vector is a vector. What's the dot product of two vectors? Notice I don't have brackets here. This is not a vector. If I do AC plus BD, what kind of thing do you have? This is a number. The dot product of two vectors is a number. I'll have students on an exam, do u dot v equals the vector 3, 7. That's a 0. That makes no sense, right? The dot product of two vectors is not a vector. All the other ones were. The sum of the difference in the scalar multiple of a vector is a vector, but not the dot product, okay? So keep that in mind. So let's do some examples here. So it says compute 3, 7 dot negative 2, 8. Right? So the dot product of two vectors, the answer here is going to be a number. What do? Right? AC, you multiply the first coordinates, 3 times negative 2. You multiply the second coordinates, 7 times 8, and you add them together. So it's 56 minus 6 is 50. That's all there is to it. Please don't make this harder than it is. So pause the video and do the second one. Okay, so the dot product of negative 1, 6 and the vector 3, 2, you multiply the first coordinates, you multiply the second coordinates, and you add them together. That's 12 minus 3. The dot product is 9. Okay. Now, you may say, well, where in the world would this dot product thing show up? That's what this next example is for. If theta is the angle between two non-zero vectors, where theta is between 0 and 180 degrees. Okay, so if you had a vector, like this and like this, and you said, what's the angle between the vectors? Your eyes want to put it here, and that's correct, because around here is more than 180. They want the answer to be less than 180. So that's the angle between the vectors. So the formula to find the angle between two vectors is cosine of the theta, the angle between the vectors. It's u dot v over magnitude of u, magnitude of v. So if you have the two vectors, computing the dot product is easy. We just did it. We know how to find the magnitude of u, and we know how to find the magnitude of v. The R formula. Okay, so it says, the example to use is, find the angle between the vectors in example A above. So that's these two vectors here. This one and this one. Now, you don't have to draw a picture here, but just for kicks, if I can, my scale is probably going to be so great, but that's not so great. So 3, 7, 1, 2, 3, 4, 5, 6, 7, 3, 7 is here. That's this vector, that's 3, 7. And negative 2, 8 is here. Again, you don't need the picture. I'm just doing this to get an idea. How big do you think theta is going to be, even from my rough sketch? I mean, even if I'm off a little bit, that doesn't look like it's 80 degrees or anything like that. Maybe 40? I don't know, something like that. I'm just doing this to get an idea. Okay. Well, there's 3 things we need to use our little formula I just erased. We need the dot product. Well, we did the dot product above, right? So we already did the dot product. What else do we need? We need the magnitude of each of the vectors. Okay, remember the magnitude is represented by the vertical bars. So I need the magnitude of the vector negative 2, 8. That's the square root of 2 squared plus 8 squared. That's 64 and 4. That's square root of 68. 64 and 4. And what's the magnitude of the vector 3, 7? Square root of 3 squared plus 7 squared. That's 49 and 9, which is, so that's square root of 58. So we already know how to find these, right? We found the dot product and we found the 2 magnitudes. So the formula is cosine theta is u dot v, right? The dot product we did was 50. And the magnitude of one of them is root 68. And the other one is root 58. Okay? So just to make punching in, save myself a little bit of grief, I'm going to go ahead and punch these numbers in just to see what that is. I'm not finding theta yet. I'm just going to punch this in and get a decimal. You should too. Make sure you get the same thing. I got this is about 0.796162. Okay, so one thing you have to be careful of, if you want to type this whole thing in one step, you have to put the entire denominator in parentheses. It's a good habit whenever you have a fraction, when you have a numerator over denominator, get in the habit of just putting it all in parentheses. I mean, you don't need the 50 in parentheses here, but it's a good habit. Just put parentheses, type the numerator parentheses, divided by parentheses, type the denominator parentheses. I mean, that's not a bad idea, because if you type this in as 50 divided by root 68 times root 58, your calculator is going to do order of operations. It's going to do 50 divided by that and multiply by root 58 instead of dividing. When I typed this in, I did 50 divided by root 68, enter, then divided by root 58, enter. I just did it as 2 things because there's so many parentheses to deal with. Okay, so how do we get theta? Cosine of an angle is a number, so the angle is the cosine inverse of the number. You see why I did this separately, because I didn't want to do cosine inverse of that and add even more parentheses. So I went ahead and did that first. So let's see, cosine inverse of that is about 37.23 degrees. I guessed 40, and it was 37. That's not a bad guess. So my picture's not too bad, actually. Okay, so there's working with vectors without having to draw the pictures.